Very good evening. Very good evening, ladies and gentlemen. A very good evening to dear children. In my hands here, I am holding an object which is made out of something which is very common on our planet. However, it does not belong to this planet. You see, what I'm holding is a piece of an iron meteorite. This iron meteorite fell in Mexico 10,000 years ago. It weighs 3 tons, and a part of it was donated. This part was donated to the Royal Institution in 1794, and I'm very pleased to be able to show you this. Now, meteorites are made of iron, and we are aware of the fact that people have been using iron, meteoritic iron, for about at least 10,000 years. That's how far our records go. However, people have been using iron, which they have been making by themselves, for approximately 5,000 years. Now, if you don't mind, I've got to give my meteorite away because it's very precious indeed, and I will come back to that later on. Now, what I wanted to tell you is that iron is something which we associate with permanence. It's something which is long-lasting. That meteorite is millions and millions of years old. The meteorite there that's in Mexico that fell, there are thousands of meteorites. The Mesopotamians knew about meteorites they used, and we know that people used meteoritic iron well before they started using iron, which they made themselves. Iron is associated with permanence. You go outside and you see lampposts, you see bridges, you see Hammersmith Bridge beautifully made out of iron, steel. You see the Eiffel Tower made out of steel. You see railings, you see road signs everywhere. It is associated with permanence. And perhaps I ought to tell you that the greatest, the most famous monument which exists in the world today of ancient iron craft made by humans is the Iron Pillar in Delhi. There it is. The Iron Pillar in Delhi, which is in North India, has been crafted by people 2,300 years ago. It's a very pure sample of iron, and it is a mystery. It is a mystery which I'll talk about, that this has survived for so long in view of what I'm about to tell you. So iron then is associated with permanence, with a longevity, with a long-lastingness. However, I'm going to demonstrate to you in the next hour or so that nothing could be further from the truth than the permanence of iron if it is subjected to the right sort of conditions. You see, I have here 2 sheets of steel. I bought these as offcuts from a metal supplier a few weeks ago. And this sheet of steel, as you see, is nice and shiny, as you'd expect it to be. But this sheet of steel here has got a sort of something which you are very familiar with. You say, yes, it's gone rusty. It's gone rusty. It's beginning to corrode. And this is not only not looking very nice, but it is actually going to fall apart over a period of time. Now, the reason why this one has gone rusty and this one hasn't, because I actually left this out of doors. I let the rain fall on it. I left it in awkward conditions, and that's why it has gone like that. Now, what I wanted to tell you about today is a little bit more about what rusting is. And with that aim in mind, I'm just going to set up an experiment for you, which takes quite a little time to occur. I'm going to take a piece of iron, comes, by the way, in all sorts of shapes and sizes. And I would also like to tell you there is a very important distinction between iron and steel. The distinction actually is a very small one. I've got in here, I've got a piece of iron, you see, which is very pure iron. It's 99.95% pure. This is absolutely pure iron. And I just wanted to show you how it comes. It's supplied to laboratories, and it's come in this very special piece of paper like this, and then in special waxed paper like this, and you're really not supposed to touch it with your fingers. You see, there it is. Now, that piece of iron, dear children, cost £25. That's how much it costs. Very, very pure iron. Now, the reason why it costs £25, it's not because iron is rare, it's because it is very, very difficult and expensive to purify iron. And when we use iron on an everyday basis, it is actually part of an alloy which we call steel. And steel is really what we have always used in our construction, in all the sorts of things that we make on an everyday basis. So from now on, when I use the word iron, I'm technically talking about steel. This here is very, very pure iron. It is hugely expensive, and it is really only used for special experiments involving chemistry. What I wanted to do, though, is to show you an experiment and to demonstrate what actually happens when iron goes rusty. Iron, by the way, is supplied in many shapes and sizes and forms. And I have here, this is commercially available, it's called steel wool, and it's used for cleaning. If you have a dirty surface and you want to clean it, this is exceptionally good. It's the same sort of stuff that Brillo pads are made out of for cleaning dishes. What I'm going to do, I'm going to cut a piece of this. It's interesting that I'm using scissors made of steel to cut the same stuff, but I'll tell you more about that later on. What I'm going to do now is to place some my steel wool inside my flask here, and I'm going to push it in. This takes a little bit of an effort, by the way, to make it fit in, and then I'm going to make it go rusty. I'm going to make it go rusty, there it is, and the way I'm going to make it go rusty is obviously by adding some water to it. So I've got some water here, which I'm just pouring in. By the way, I have to admit in all fairness that the water has had a little bit of salt added to it. It's seawater technically, and what I'm going to do now, I'm going to shake it up very, very thoroughly in my flask. So if you don't mind, this is just to make sure that the piece of steel wool is getting thoroughly soaked. Now, the only other ingredient in this flask is air, of course, because the flask is full of air. Air is all around us. I have now shaken up my flask here. Maybe I'll add a bit more water. You must excuse me, I've got a supply of water here. This is just to make sure that we give it a thorough soaking. So we're just going to There'll be out that, soak it like that. And now we're going to turn it upside down to just let all the water drain out. So we're going to leave it here for just a few minutes like that. You see, it takes a little while for the water to drain out. And then very shortly after that, I'll come back. When iron goes rusty, actually, it combines with oxygen. That's what chemists have discovered. And when it combines with oxygen, it changes its color to that orange form. And I've actually got some powdered rust here. It's a light brown color there. This is now draining out. As I said, I'll come back to it in about 5 minutes or so. But what I wanted to tell you is that when iron combines with oxygen, that can also be interpreted as a process of burning, because when things burn, they combine with oxygen. Now, you see, if I took a nail, I've got a nail here, and I said, oh, shall we set the nail on fire? I can put it into the candle. So that's a stupid thing to do, because obviously an iron nail can't catch fire. So there I'm putting it in, of course, and there it's getting a bit charred on the end, but that's just so no chance it's catching fire. However, allow me to show you some powdered iron. I've got some iron here in the form of a powder, and I'm just going to sprinkle that. It's not a huge amount, it's nothing spectacular, but look at those tiny little sparkles that are coming off. See? Now that you see those tiny sparks there, the iron is actually amazingly catching fire. See, it's made a few little sparks there, and we can see therefore that's very interesting. But you say, okay, lots of things can spark up. But let me now show you another experiment with a piece of steel wool here. And if you don't mind, for this purpose, I'm going to just put a pair of gloves on and also get my tongs. So please excuse me. And I'm going to see what happens when we place a piece of steel wool in our candle flame. So I need to take some precautions here. You must excuse me. And then I'll come to the front so that you can see it better. Now, as you know, we do have a lot of things here, and I'll just kick this balloon out of the way. And I just wanted to show a surprising effect, you see, of putting this is, again, iron, the same stuff that the nail was made of, but we just put it on a candle flame. And there you see, okay, that's nothing special, it's glowing. But actually, if we start waving it around, you see it starts to glow even better. And so, oh, this is very pretty. you see. And you say, wow, isn't that amazing? Now, what's actually happening, dear children, the iron, because it's in the form of a steel wall, it has a very large surface area, and therefore it is reacting with the oxygen. This is generating a huge amount of heat, by the way. It's actually very hot. So what we've done is we're combining the iron with the oxygen in the air, and it is actually visibly burning. Now, this is a very different type of flame from the flame which you get when you burn a candle or you burn a piece of wood. And the reason being is that the product of this combustion process here is actually not a gas, as most combustible things produce are gases. It is actually a solid. We are actually converting the iron here to the oxide of iron, which is a solid. And it is a characteristic of all metals when they burn, if that's an appropriate term to use, that they actually make a solid oxide. If you don't mind, I'm just squeezing the oxygen out of that to make sure it doesn't continue burning. And very shortly, we'll have a little sweeping session to tidy up. If you don't mind, I'm going to put this into the bin. Now, for my next demonstration, I'm going to set fire to a much more robust piece of iron, and that is a piece of steel tubing. Allow me to show you what the steel tubing actually looks like. This is it. This is a piece of mild steel tubing, you see, which I also bought. And you know that if I put that in the flame, that's not going to catch fire under any circumstances, because this has a very large bulk. And allow me to explain to you the reason why the wool caught fire and why the powder caught fire. The reason is to do with surface area. You see, when things are powdered, they have a very, very large surface area, so therefore the flame can easily access it and get the combination with oxygen to occur. But when you have a large chunk of iron or a nail, then the surface area is very slow, very small, and therefore that same process with the candle will not give you a desired effect. However, what I'm going to do now is I'm going to actually set this on fire. I'm going to cause it to burn by a very different type of technique. I'm not going to apply a flame to it. I'm going to actually apply friction to it. Now, you see, friction is something, if you rub your hands together, you can feel them getting warm. My hands are definitely warming up, and if you can rub them hard enough, then you'll feel them getting warm. Now, what I wanted to tell you is I have a special machine here. This is a tool which is used in industry, etc., and it's called an angle grinder. And what it consists of is a motor which is connected to a disc. You see, this disc here is made of an abrasive material, and it spins around amazingly fast. Allow me to switch it on. I have to warn you, this does make a noise. There you are. Now, you see, that's what we call an angle grinder. And when that wheel spins around, it spins around so fast that the friction it generates is enough to melt through the steel and also to set it on fire, which is what I'm going to do next. Now, for this purpose, I'm going to introduce Domonkos. Can you both come forward? Domonkos and Marjolaine are two pupils from Highgate School in North London, and they've actually been helping me to prepare the talk today, and they'll be taking part in many of the experiments. So, Domonkos, this is, if you could kindly put on now, you must actually, we're always going to be putting on various safety gear because some of these experiments are actually quite dangerous. So I'm just going to put on my goggles here. Dom will put his on. And what we're going to do is I'm going to set fire. I'm going to grind through that piece of mild steel. And he's going to catch the bits that come off, you see, the dust that comes off. And we'll examine it very shortly. So I'm going to first of all just do a trial run. I do warn you, this makes a lot of sparks and it's incredibly noisy, but I think we must observe these things in action. So here we go. I'm just going to do a trial first to see where the sparks go. So, is that okay, Dom? Right, Dom's now going to collect the sparks. Hold it in such a way that people can see. That's very good. Are you ready? Okay, Dom. Thank you very much. So we now have to show you, see, we've done something which no builders or no engineers would ever bother doing. We've actually collected the sparks. The object was not to cut through the iron, but to see what it makes when it burns. You see, and there it is. There is that little bit of powder there. Now that you see, what's interesting is that powder which I've produced there has a black color. It's combined clearly with oxygen, and yet it's got a black color. It's not brown like rust, and I will very shortly explain that. In the meantime, we have drained out our water from there. I hope we've drained it out. And I'm now going to connect this up to a tube here, and I'm going to invert it in a beaker full of colored water. And I very much hope that we'll be able to observe the rusting process. Now, dear children, rusting takes a long time. It doesn't happen instantly, etc. So I'm attempting to show you a reaction which normally takes several weeks out in the open, but I'm attempting to show you just a hint. Maybe it'll take half an hour. What's going to happen is this. As the oxygen is reacting with our steel wool in there, which has got water on it, gradually the oxygen will get used up and it will create a partial vacuum in there. So the air pressure will hopefully push down upon the water, the colored water which I've got there, and hopefully you will see it rising up the tube. But this will take up to half an hour. So we'll leave it standing there, and I do believe that we're just off the mark on that. Allow me now, Dom, could we please take this away and take that lot away? Thank you very, very much indeed. And I will proceed on to the next demonstration, which consists of showing you more iron burning, obviously, since we're on this theme. And I wanted just to show you, first of all, that iron can be used in pyrotechnic. This idea of sparkling, I think you think those sparks were rather good fun. And they are, of course, used in commercial sparklers. Now, I have two sparklers here, and I'm going to ask Dom and Marjolaine to burn one each. This is just to show you, you know, they're fun, they just make that, etc. Could you both please just light a sparkler each in the candle flame and just hold it? You've all seen this before, and what's interesting about sparklers is that actually you don't have to wear safety spectacles. Children play with these at parties, you see. So there are just two sparklers burning like that. Now, while those sparklers are burning, I wanted to show you another application for a pyro. So that's just, you see, sparkler that contains iron filings in it, and it's burning away, and it's very pretty, and it's safe, and all the rest of it. And indeed, what's also interesting, you'll notice the sparks don't actually burn your fingers. They're holding them, and the reason is that all of the thermal energy is consumed during the actual burning process. They're very, very tiny indeed. The amount of heat energy is so small that it doesn't actually affect you. I just wanted to show you now just a couple of other interesting demonstrations, using this as purely as a pyrotechnic effect. And I want to show, first of all, a very small sample of gunpowder burning. You see, I have some gunpowder in here. This is black powder, and I wanted to show you how black powder burns just on its own, without any additive, you see. There's quite a decent charge. There's about 5 grams there, and you'll see how this is gunpowder burning on its own. I've just got to double check, by the way, that I do have there we do have the other one. Actually, my goggles are steaming up. I'm so nervous. I think I'll just carry on. I'm sure it'll be fine. I do about 15 pairs of goggles, by the way, one for every experiment. So there we are. We'll put this one on now. Now, please watch carefully. Watch carefully as we demonstrate some standard black powder burning. This is normal gunpowder. And there you are, a nice little puff of smoke going up into the atmosphere, etc. But please allow me, you see, chemists and pyrotechnicians are always interested in improving things, you see. So what some people somewhere, they noted these iron sparks burning, etc. Notice the water is beginning to creep up, by the way. They noticed the sparks burning, and they thought, let's try adding some iron filings to gunpowder, and let's see what effect that makes. So that's what I'm going to show you next. Now, I have to take great care, by the way, because these things do get They sort of go all over the place sometimes, the spark. This is now gunpowder, but mixed with iron filings. Once again, it's a fairly small charge, but it does have an amazingly pretty effect. And I'm going to just set this on fire and watch carefully. So watch carefully, because what you get is a beautiful shower of orange sparks in addition, and it's also slowed down in its process of burning. So this is now gunpowder with added iron filings, or should I say iron powder, to make it as a pyrotechnic effect. And you see, there was a whole little shower of orange sparks which came out. And you see they've burnt little holes in the thing, but that doesn't matter. That's part of the demonstration. We do expect to get through quite a few bits of paper and all sorts of other things. So what I've demonstrated for you now, you see, I've demonstrated for you a variety of applications in which iron is turned into iron oxide. And I wanted just to show you, I've actually got 3 different samples here of iron oxide already. This one is rust. That's powdered rust. I got a rusty sheet and I scraped the rust off, and that's how it looks, a light brown color. This here, this oxide here is actually called ferroso-ferric oxide. It's tri-iron tetroxide. The chemical formula is Fe3O4, 3 atoms of oxygen combined, 3 atoms of iron combined with 4 atoms of oxygen. The formula, by the way, for rust is Fe2O3 dot H2O. It's iron oxide, Fe2O3, combined with approximately 1 molecule of water. Indeed, if you heat this very strongly, you will end up with this. This is calcined iron oxide which has had the rust, which has had the water removed, and its formula is Fe2O3. I wanted to tell you that these are relatively stable and we can examine them, but there exists yet another type of iron oxide which no one ever sees. But we're going to see it today for a very, very brief short period of time. Now, allow me to tell you, what I've got here is iron carbonate, chemical formula FeCO3. Now, when you heat this very strongly, as Dom is going to do, maybe is that flame strong enough, Dom? We've practiced it a few times. We have to use quite a strong technique. It decomposes into FeO and CO2. What's rather unusual about this iron carbonate, it comes in, I think it's mixed in with a tiny bit of sugar, so it makes a sugary smell. I'm not quite sure why that is. But Dom, can I leave you to it? Because I know you've done this before. And in the meantime, I will be explaining a few other little bits and pieces. Dom, while you're doing that, and what I'm going to tell you what he's going to do, and then we'll relate it to a little theory. When iron carbonate is heated, it decomposes to make iron 2 oxide, FeO. Let me remind you of the formula. This was Fe2O3, Fe3O4, Fe2O3 dot H2O. But when this is made, its chemical formula is FeO. It is a very unusual and unstable type of iron oxide. We call it pyrophoric iron oxide. And what that means is that if you pour it into the air, it spontaneously catches fire and sparkles to make iron oxide Fe2O3. Pyrophoric meaning it catches fire. Carry on heating that until you're ready. Don't dope enough. But may we please have the next slide, because I wanted to explain a little bit about this curious feature of iron and its chemistry, the reason why iron demonstrates this curious ability to link up with different atoms in different ways, different elements in different ways. Now, there in front of us is the greatest achievement of the human race in terms of our understanding of the nature of matter. This is a periodic table of the chemical elements, which I'm sure you all recognize. And what it contains is all the building bricks of every single substance. This is a remarkable achievement of us human beings, that we've been able to organize all of these in nice rows and columns. Now, Fe, by the way, is the Latin for iron, ferrum. Before chemistry, we had alchemy, and alchemists used the Latin tongue, and many of their words still occur in today's language. So there is iron in the middle, and you notice it's in the middle of a large group of elements, which are all colored in yellow. Now, those elements, dear children, are called the transition elements. They're called the transition elements because, broadly speaking, elements are divided into 2 categories: metals and non-metals. All the green, yellow, purple and blue ones are the metals and the white ones at the bottom, but just the top right-hand corner with the white ones in the column on the right, those are the non-metals. That's a very, very approximate division. Now, I'm being a member of the transition metals. What they specialize in is doing all sorts of chemical, undertaking chemical reactions. They're all metals, engineering metals, but they undertake a wide variety of chemical reactions. I'll quickly summarize them because I don't want to bore with theory to it, but they have variable valency. In other words, they can combine in a variety of ways with one element. Variable oxidation state. They form colored compounds, they form complex ions, and they act as very good catalysts. I'm going to show you some of each of those. In the meantime, so can we have that slide off now, please? In the meantime, I'm going to, Dom will get ready to do that. I am going to start off an experiment here. You carry on, dear Dom. Are you ready? By the way, if it's possible to turn the lights off while Dom does this, and he's got a little watch glass on the bottom, you'll notice. If you dim the lights, then I think you'll find this very, very much more instructive and enjoyable to watch this. So, Dom, you carry on at your leisure, sir. And there you see, that you see is iron oxide FeO being spontaneously oxidized into Fe2O3. Thank you very much indeed, dear Dom. Now, could we kindly... now, I'm setting up another experiment up here, which involves the use of iron nails. And what I wanted to tell you, because this is the next topic I move, we'll have a look at the remnants in that glass in a second. We'll have a look at the remnants in the glass in a second. But I just wanted to tell you, I'm about to do an experiment. I had a piece of cotton wool here, which seems to have mysteriously disappeared. It's not the end of the world if I can't see it, but if I find it, I will find... Is it there somewhere? Oh, there it is. Thank you so much. Thank you so much, my dears. This is right. Here we go. Now, what I've done in here, I have in here some nails. This is half full of iron nails, and what I've done, I have poured about 250 mils of dilute sulfuric acid. But I'm going to be generating hydrogen gas from this, which will fill this balloon in due course. It takes about half an hour. I may have put too much acid in. The thing is, we have to move on. Now, what I'm going to do now is I'm going to show you some reactions involving iron, and among those is ones in which hydrogen is produced. Now, this has a very important story. The gas hydrogen was officially discovered in 1770 by Henry Cavendish, 1777, and Henry Cavendish recognized it and identified it as an element. But the honest truth is, people had been preparing hydrogen gas since the medieval times. They reacted it by mixing this substance here, which was then called oil of vitriol. It was made by burning sulfur, and sulfurous fumes were produced from various minerals and dissolving the fumes in water. And they reacted it with iron. And they found out that if you react oil of vitriol with iron, then the iron starts to bubble away there, and we're just going to let the first few bubbles escape, and we're going to allow this to carry on bubbling. Now, very shortly, hydrogen gas will be produced. I had iron powder in there, and I had iron nails in here. They are both reacting with the same substance, sulfuric acid. Now, this particular reaction had a huge significance in the year 1783. As you all know, in 1783 was a great, great date in the history of flight, because that was the first time that man successfully launched balloons with humans in them and flew into the sky. And there were two types of balloon. There were hot air balloons, which were made by and used by the Montgolfier brothers in Paris, but times were very competitive, and another Frenchman, Jacques Charles, made a balloon filled with hydrogen. Now, these balloons were ginormous. They were almost the size of this auditorium here. They required tons of iron nails and sulfuric acid. It was done on a huge industrial scale. And when these balloons were launched, they caused a huge sensation among the public. So what I'm going to do is to actually use their technology, using iron nails and sulfuric acid to fill this balloon with hydrogen. Now, it takes approximately half an hour to fill, so it grows very slowly. This one, by the way, notice our purple liquid is rising up the tube. And what that is showing is that the iron wool is going rusty in there. It is absorbing a vital part of the atmosphere, which we know is oxygen. But you see, these are very easy to demonstrate today. It took thousands of years. It was Lavoisier who was the first, but he was a French chemist, again at the same time as the Montgolfier brothers. There was a huge amount of exciting chemistry going on there. And he was the person who recognized that oxides of metals were solid, and he was able to prove this. Now, can I ask you, Dom, and maybe Marjolaine, to burn off a few of those jars of hydrogen, a few of the... and the object, by the way, of this experiment, dear children, this is the point I'm trying to make. The objective is not to make hydrogen. It's to make what's going to be in that flask. The object is to see what the iron turns into. But if hydrogen is being produced, we must not waste it, and therefore we shall burn it. And so that will be the side, that will be the, please feel free to burn off as many jars of hydrogen as you like, provided it comes off. And in the meantime, I will concentrate on our next experiment. So you feel that one probably won't have any hydrogen in. By the way, they have not practiced this at all, so this is just doing things from first principles. But I think I have every confidence that the first one may well be full of... Yeah, that was pretty pure hydrogen. Can I, by the way, while I'm demonstrating, I'll just show them a few tricks, then they can then have a little more. Can I show you a few tricks, please, Dom and Marjolaine? Right. The first thing is this, that a good idea will be, when you keep that burning, that's very handy. If you actually mix it with air, okay, then it will make a slight pop, you see. There you are, far more fun. See, so I just wanted you to, while I'm doing that, you can enjoy this. And put a lid on, you see, like that. So the point is, pure hydrogen burns. So when you actually do the experiment, well, it's about 50%, about half full will make a pop. If it's any more than that, then it will decrease until one which is pure hydrogen, which is one you first burn. That was absolutely, that makes virtually no sound. Well, please, I want you to carry on. Now, the reason why they're carrying on, because I am now going to do the next experiment here. Now, I'll repeat once again, the object of this experiment is not to make the hydrogen, it's to make what's going to be in there. And I will tell you straight away, it's iron sulfate, FeSO4, otherwise known as green vitriol. And if you look carefully around, you'll see some standing around on the bench. But what I'm going to do here, at the back here, is a much more tricky. You must carry on regardless, and I will ask you to, for one moment, to break the demonstration there, and we will, and then I will tell everyone what's to concentrate. But you carry on for a little bit. Now, what I wanted to tell you here, I've got some iron nails. I hope you can all see them in this flask. Let me just hold them up. There's some iron nails in there, and I'm going to make iron, a different type of iron, in this flask. This is going to be what we call iron 2, Fe2+, pale green as it will be, but this one here will be iron 3+, which is dark brown. Now, Dom, can we let's just take a short break. This is purely so that we can all focus on, we can let that bubble over, and you can return to that in just a second. And I'm going to now demonstrate for you what is a reaction in which well, I'm hoping works out to be good fun, because I'm going to prepare these two flasks. This one will hold our green solution being made, pale green solution being made in there, and this flask here will hold, hopefully, a dark brown solution, which is iron 3+. So two different oxidation states of iron, typical of transition metal chemistry. Now, this one reacted with sulfuric acid, but this one we are going to react with a strong solution of nitric acid. It's a relatively concentrated solution, and for this purpose, I will, of course, be wearing safety spectacles. Now, I did actually put some, I had some less sort of, how have we got those? Can I borrow your ones, my dear? I've got about 6 pairs of these. Thank you very much indeed, because we don't actually need the heavy-duty ones. Now, what I've got here is concentrated nitric acid. And in this experiment, we react a solution of 50% nitric. Now, nitric acid is a powerful oxidizing agent, by the way. So what it does is it oxidizes Fe to Fe3+, which is, I'm adding water to it to dilute it down to to dilute it down to about 50% strength. And when this happens, this is rather quite dramatic, which is why I've cancelled everything over there in order that you can watch what goes on here. We can put this to one side and that will be taken away. And this too will be taken away in due course. Is that okay, Dom? Let's watch this first though, because I hope this yields. Now allow me to tell you what happens. When iron reacts with concentrated nitric or 50% nitric acid, it releases a huge amount of a dark brown gas, nitrogen dioxide. And it also gets very hot indeed. It's what we call an exothermic reaction. That nitrogen dioxide is also very poisonous, so we mustn't allow it to escape. So what I've got here is what we call a scrubber. It's technically, that's the engineering term. This scrubs out the acid, gas, nitrogen dioxide. It's actually water, almost pure water, with a few drops of universal indicator and a couple of drops of ammonia to give it the alkaline color. This here is a flask which has got just a few drops of strong ammonia solution, and this one here is a flask with ammonia solution in it diluted with water. Now the purpose of all of this is to absorb our dangerous toxic nitrogen dioxide gas and neutralize it. But there is a second purpose. This here is a tiny, tiny amount of solution, which will, when it gets hot, half of this will evaporate away and disappear. So what I've done in this experiment is a physical effect as well. Once the chemistry is over, this will be very hot indeed. I will then cool this flask down by pouring water over it, and hopefully, as it cools down, it will contract, and all of that water will get sucked through into there and dilute our solution to make a flask half full of a beautiful brown liquid. Now this one in the meantime is getting slightly over the top. Dom, if we could just monitor that on an occasional basis. They heat up and they froth up, and at a certain stage, Dom, you'll be able to disconnect it, okay? Just swirl it around every so often. But I think we should all try and watch this now, and I hope it works. Give it a swirl around, Dom, and let's go. This one, by the way, all happens in a space of 3 minutes. So I'm just double checking that all my joints are tight, and you're going to see quite a lot going on in this reaction. So there goes our nitric acid in there. Initially nothing happens, but within a small space of time you see very, very vigorous bubbling. So there's our brown fumes of acid. Now watch the color here. Purple, green, and now gone to red. So we now have red, it's gone acidic. We have white fumes here of ammonium nitrate, which is relatively harmless. But you notice there's not a single smidgen of our dark brown acidic gas. So this experiment is totally safe. This is ammonium nitrate with a bit of ammonia added in, which is perfectly satisfactory at these levels. In the meantime, Dom has cooled down our flask, which is reacting. Can I just show it to everyone, Dom? It's frothing up. It's frothing up. And the way we cool it down, Dom, we simply add water to dilute. Okay, so I'm just going to dilute the reaction down. And you say, but Szydlo, you said it's going to be a nice green color. I can't see any green color there at all. It's a murky black color. Of course it is. But you see, that murky black is due to the excess of iron filings. What I'm now going to do is to pour it through a filter paper. Now, the filter paper should hopefully filter out the solid particles, and with a bit of luck, we should get a beautiful pale green solution of iron 2 sulfate. Now I'll leave that running on the front here. We'll leave that filtering, and Dom, I may ask you or Marjolaine to add some more once the level has gone low. In the meantime, let us examine our reaction here. The reaction has now almost finished. All the acid will swirl it around a little bit. Woof, that is very hot indeed. Probably about 45 to 50 degrees centigrade. That's very hot indeed. And you will notice that the fumes have stopped coming out. This is where we start the fun with the pneumatics. We're now going to conduct a physical effect. I'm going to cool this down, and as I cool it down, you'll notice it will hopefully suck back water from there. There we go. It's now sucking water back from there because this is cooled down and the gas is very soluble in water. We're sucking, the ammonia is going back through to here, and we now have a flask which has got a significant amount of a very beautiful dark brown iron 3 nitrate. So in this flask here, we have now in its stages of filter, you could begin to see the beautiful green color becoming apparent there. And here we have a flask which is pretty brown in color, and that is now contains iron 3+. Now, you would think that this is now totally safe, that I've got rid of all my nitrogen dioxide, which is deadly poison. But actually, please watch carefully, because when I take this off, you will notice suddenly the appearance of dark brown poisonous nitrogen dioxide. Please watch carefully. And there it is. You can see the fumes coming off there. And if you thought that was the only flask with it in, then there it is, can you see? And it's continuing to suck more water. Now, ladies and gentlemen, dear children, the reason why this has happened, because actually in this experiment there are 2 gases produced. One of them is nitrogen dioxide, NO2, and the other one is nitrogen monoxide, NO. And nitrogen monoxide, which is here, there, and there, has no color whatsoever. It's a colorless gas, but it's unstable, and it immediately reacts with oxygen to make nitrogen dioxide. A little bit similar to what you saw with FeO going to Fe2O3, the same sort of thing. So if I disconnect that, then we'll get the 2 liter. Can you see there the brown fumes? But I'm not going to pursue on this. Thank you very much. And indeed, and what I'm going to do now, the object was to make our brown solution, and I shall now replace this flask here, and I will ask, maybe we can leave it here for the time being, but we will later disband this. Now, here we have this murky solution you see here, which is essentially iron 3 nitrate, and when we filter this, this should give you a very, very beautiful brown color, dark brown color of iron, in what we call a different oxidation state. So here you see, out in these powders here we have iron. Oh, we can have a look, you see, as the black iron oxide fell to the ground, it oxidized and it's gone dark red, you see, which is the color of this. So that's Fe2O3, which is there. So that's our product, which we've managed to collect down there. So in the meantime, our steel wool is rusting and the water is rising, showing the consumption of oxygen. In the meantime here, we have now got 2 kinds of iron in solution. This is iron 2+, and this is iron 3+, both made by reacting with acids, but in this case with very different acids. One using nitric acid, which is a powerful oxidizing agent and is able to get that extra combining power. The other one being sulfuric acid, which merely achieves the Fe2+ oxidation state. Now, in the meantime, our balloon is filling. We're well on the way, but we've still got about another 20 minutes. And now I wanted to talk a little bit about the solutions that we have made. I'm just going to I need to find a couple of, we need to be able to allow these to carry on dripping. So that one can go back into that flask. We'll put this one back into this flask here. So we've got our 2 specimens of solution, and I just want to show you now a few chemical tests to distinguish between these 2 types of iron. And for that purpose, I've got 4 solutions here, which are used commonly by analytical chemists to show the one type of iron from the other type of iron. And I'm going to start off with each of these here. I have some sodium hydroxide solution. And what happens is, with sodium hydroxide solution, the 2 different types of iron make a different colored precipitate. So one is iron 2. I'll just pour a few drops in from here, and you should see a dark green gelatinous precipitate form. There it is. It's a sort of murky green gelatinous precipitate of iron 2 hydroxide. This one will obviously make a brown precipitate of iron 3 hydroxide. There it is. And we call it a gelatinous precipitate. It looks like a sort of a jelly that's settled down on there. Now, in the next one here, I've got a solution of potassium ferricyanide. I can't remember which is which. There are 2 solutions, both pale yellow in color. One's potassium ferricyanide and the other is potassium ferrocyanide. But what they do, they very nicely distinguish between the Fe2 plus and the Fe3 plus. And you'll notice the color, they're very dramatic color changes when the reaction happens. So I'm going to put some Fe3 plus in here, and we'll see whether that's the dramatic color. And there it is, a beautiful, intensely deep, this is called Prussian blue. There it is, it's a very dark blue color there, and we've got it there, you see. That's the Fe3 plus. Now, with this one here, it shouldn't work, but it does because the Fe3 plus is actually mixed in with a bit of Fe2 plus. And there you see, we are getting the same thing here. However, if I take, I don't have my bottle with me, but I'll explain a little bit more. What we've got here is actually Fe3 plus with a small amount of Fe2 plus, which that has shown to be the case. However, if we now do this one here, a few drops of it, this is the other one, you again getting Prussian blue in this case, an intensely deep blue. Oh no, silly Szydlo, I should have done this one. I should have added Fe2 plus. Oh, dearie, dearie me. Let's have a look. That's the Fe, and I've messed this up. Dom, could you do me a favor? Run to the department and get both the ferrocyanide and the ferricyanide, because I've muffed it up. Please excuse me, one makes mistakes when one is in a hurry, and I'm in a hurry. Now, I wanted, the next one here, I've got thiocyanate. And thiocyanate is a very spectacular way, because this one distinguishes, this one you only need 1 or 2 drops of Fe3 plus, and it shows you a brilliant dark red color. So please let's just watch this here and see if we can get this. There we are. There's this intense dark red color. This is, by the way, what we call complex ions. Thank you very much. Dom, if we can basically, I'll tell you what, if you just get rid of those 2 down in the bucket, and we'll put some ferricyanide back in, we'll repeat that experiment. So that, thank you very much indeed. So there is Fe3 plus in there, and if we put the that dark red, if we put some in here, and if we put Fe2 plus, this is me getting confused. Fe2 plus, it should have no effect at all on this, you see. Shouldn't produce any of that red color. So there it is, you see. I'm adding Fe2 plus there, and it has no. So this is a very definitive test for the iron 3 ion, this intense. Have we got those 2 beakers there again? Thank you very, they're messy, it doesn't matter, we'll rinse them out. We have everything on hand, my dear boy. Look, I've come here, I'm prepared, hopefully I'm prepared for all sorts of situations. Thank you very much indeed. One of these clearly was, just rinse those down into our bucket, waste bucket. Thank you very much, Dom. We'll just quickly have a go and see if I can get this one to it. This is ferricyanide, which works with, which should turn an intense deep blue with ferrous. So we'll put the Fe2 plus in there, and well, we'll just see what happens. I think there must always be a spirit of enterprise and a little bit of going into the unknown. There we are, we have an intense blue. What happens in here? Don't bother. Okay, let's try the other one. Rinse this one out. I'm getting myself confused, you know, with ferry and ferro. No, it is very confusing. We'll now try the same with these 2. A little bit more water, Dom, you're becoming a master of the secrets. Now, allow me to, oh, by the way, while we're on that subject, I have another beautiful experiment for you. A beautiful experiment. I'm going to grow you some plants now. Some plants made out of iron 2 plus and iron 3 plus. I have in here a substance which is called water glass. It's actually a chemical, and we can make chemical gardens with this. And this is probably the most beautiful experiment you're going to see today. We'll just give it another little rinse out, Dom. I've totally forgotten what I was doing there, but I'm sure we'll get there eventually. Now, I'm just going to, what I wanted to tell you is what this does. By the way, these are beautiful crystals of iron sulfate, which I've grown for the past few days. I think they're so beautiful, I just wanted to show them to you. And that's what's actually being made in there. If you allow this solution here to crystallize, those are the crystals it makes. But if we pop some of these crystals in here, a small quantity, by the way, they're totally harmless, a couple of these crystals in there, and a couple of smaller ones, because those are the large ones. Whoops, you see, I'm getting my lids confused here. Let's just go there, and a few smaller ones down here. A few smaller ones here. This is iron 2 sulfate, but in a larger surface. It's got a much smaller, so larger surface it'll go happen. And I'm now going to add to it some iron 3 chloride. Now, iron 3 chloride will give you hopefully some brown plants. And what will happen in the next half hour, you'll see a beautiful chemical garden made of iron. And there'll be 2 kinds of iron, brown iron and green iron. And children, even if you've forgotten all the chemistry, just remember that iron has 2 colours, green and brown. And that will be very good enough. You'll then say that you learnt a lot. But this, I very much hope, this will show you this, demonstrate this in the most beautiful manner. Now, in the meantime, what was I going to do, Dom? Because I've forgotten. Sorry, which one's going to be this one? Ferrocyanide now, yeah? Let's try. I think one must always, I'm trying to get you one where what happens, it goes a beautiful deep blue in one, but a very, very beautiful aquamarine in the other. So this is our Fe2+. There it is. I've got the result. And here you see, no, that must, oh no, the other one. Are you sure? No. Wasn't it meant to? No, this is the one that'll go dark blue. Doesn't it? No, I'm sure this is right. Oh no, I am stupid. He's right. I'm a disaster. There we are. Look, I've got it now. By hook or by crook. I hope you've all understood. As you see, I don't, but thank goodness I've got intelligent people. No. Don, thank you. I'm stupid. I should listen to my students. Thank you very much. I'm sorry. But look, don't you think that's a beautiful blue? That's another complex. I have no idea what it is, but it's beautiful. I just wanted to show you some nice colours. I don't understand what I'm doing. I can't even do it, but we're getting a result. Now, let's hope that I can show a little more intelligence. And my dear Dom, could we just lob this lot into the bin now? We've got to clear some space now. Let's have you must excuse me, a little tidy up session now. A little tidy up session. Can we just lob that lot all into the bin, please, Marjolaine and Dom? Thank you so much indeed. And put those to one side. A little tidy up session. Now, can you see our beautiful garden growing, dear children? I'm not going to disturb, but look, our iron is rusting and our balloon is growing. So we are actually, I will hold it up later. And I promise you things are working. We're getting more success than not success. Now, let's put that away. Now, as I was saying, so we've got the ferrocyanide and the ferricyanide. You saw colour changes. That was the important thing. And they tested for something, and I know in theory, but in practice, it's all. Look at this. Isn't it amazing? It's sucking this up because the oxygen, as this is rusting in front of your own eyes, it's sucking the water in to replace the oxygen which has been consumed, and as it's turning to a solid. Now, what I wanted to show you next is a very beautiful reaction. I told you that the transition elements have these various characteristics. I'm just going to throw this ask you to throw that into yes, if you could take that away, that would be fantastic, and put that in the blue tray, which is in the green room. Thank you very, very much indeed. Now, what I wanted to show you next, which I'm hoping will be a successful experiment, is a beautiful redox reaction. It's a reaction which Fe2+ reacts with permanganate solution, which has this beautiful dark purple color. I hope you can see. It doesn't matter if we spill a little bit, but it has this beautiful dark purple color. And excuse me, this is warming up a little bit. It's getting a little bit warm. We need to cool it down, but Dom will soon cool that down for me, and all will be restored. Because if it allows, it gets very hot and it froths up and it all goes into the balloon. But we should be okay. We're nearly ready for launch, by the way. We're nearly ready for launch. Now, this one here, Dom, could you just control that and shove it into a beaker? Put the beaker on top so that people can see. That's what we call quenching a reaction. It's getting very hot indeed. So it's not actually that hot yet, but it will be getting warmer, and that will just prevent it, hopefully, from getting a bit too excited. So we can gradually keep an eye on that, dear Dom, because we'll whip the balloon off if it looks dangerous. I just wanted to show this reaction here, in which we've got some iron 2+. Look, just a tiny bit left in there, and hopefully a couple of, because you know I'm short of glass rods. I'm a bit short of glass. Oh, I'll use a thermometer. We could use a thermometer to stir, you see. And there we are. I wanted to show, this is a beautiful reaction. It's called a redox process, in which we take Fe2+ and we add it to permanganate ions, which are purple, and you should get a very, very spectacular color change. And this becomes converted to Fe3+, you see. Remember, yellow, green going to brown. So here we go. Please watch. I'm going to add just a squirt in there and swirl it and see if anything happens. Nothing yet, you see. But it does, as I said, this won't happen immediately. There we are. Give it another swirl around there. And we're getting there. We're getting pale, you see. Our redox process is taking place. And then another squirt there. And finally, we're so close. Let's just lob the whole lot in. Damn it, this has got to work. And there we are. And there you are. Now, and you say, hang around. Szydlo, you said it's going to go pale brown because we've made Fe3+. Well, the answer is we have made Fe3+, but it's so dilute that we can only show its presence with the magic thiocyanate test. Now, is it possible that I've got thiocyanate in there? Do you think that might be thiocyanate? Let's take a risk. I'm taking a risk. I've lost control, but I'm hoping, you see, this doesn't look, but if we squirt that, maybe you'll get a dark, So you see, we've proven that we've made Fe3+, you see. So we've actually know this to say is that. So you see, this doesn't appear to have Fe3+, but this, you see, and this is chemical analysis. Chemists have developed fantastic techniques of being able to detect tiny amounts of substances using very, very, very sensitive chemicals. Thank you very much. That was, thank goodness we got that one. Now, I wanted to show you the next one. The next one I've got to show you. Now, Dom, are you keeping it? Sorry? No, it's not quite ready yet. We're very nearly there, Dom. A few more. I reckon that's got another 10 minutes to go yet, okay? So keep it, see if you can. I think it's fine. I think we're under control. We're not going to go over them. Now, I wanted to introduce you next to a chemical reaction, which is another characteristic of these transition elements, because iron represents transition metal chemistry in the most excellent way. As I've said, the idea that it can form these two oxidation states, Fe2+ and Fe3+, green and brown. The fact that it can undergo redox reactions, it can easily change from one to the other, as I have just demonstrated there. The fact, now, another important characteristic of transition elements is their ability to act as a catalyst. Now, that means it can speed up a chemical reaction. Now, what I wanted to show you here, I'm now going to pull out 3 flasks, three bottles, you see, and in these 3 bottles, I'm going to show you a chemical reaction using these 3 bottles, and I'll tell you exactly what I've got in them. And I'm going to show you a chemical reaction which is very beautiful to look at, but which we will then do in a controlled manner using iron 2+ as a catalyst. By the way, I've got some sort of neat stuff here prepared, iron 2+ and iron 3+. I hope you can all see iron 3 or red iron, brown iron and green iron. Now, what I wanted to show you first of all, is a chemical reaction which doesn't involve iron at all, but it's a very, very beautiful reaction. And this is the reaction between potassium iodide solution and acidified peroxide. I'm just going to pour, this is to show you what we are going to be demonstrating as a catalysis. So there's the reaction itself. There's nothing's happened yet, but if I add to potassium iodide solution some acidified peroxide, you should observe a beautiful golden color appearing, which is iodine. So a dilute solution of iodine, and there it is, you see. So that there is a dilute solution of iodine. Now, it so happens that it's possible to reverse this reaction and go back from iodine, which is brown, to iodide by adding sodium thiosulfate solution. Now, this is a fairly complicated redox reaction, but you don't have to understand it to enjoy it. I certainly don't understand it, but I enjoy it. So here we are. I'm just pouring in, and you'll notice a little bit, and there it goes. The color has just to go, and the color has gone. However, please watch. As you leave it, you'll notice that the color starts to come back again, and it returns, you see. And this is a reversible reaction, you see. We're disturbing the equilibrium in chemical parlance. Now, I think you'll all agree that the gold color is very beautiful, but it's not exactly a sharp and strong color. So what we can do, we can intensify the color by adding an indicator. In this case, it's starch. And if we add some starch to that, you see we get a dark blue color. Officially, it certainly is dark. And we can repeat the experiment by adding a little thiosulfate to it, you see, by adding a little thiosulfate and making the dark color disappear. If I add enough, hang around, let's just see. Yes, there we go. Now, but if you watch it though, you see, at a certain moment, suddenly the blue color will reappear. Et voila. Et voila. Now, you see, what I'm demonstrating, ladies and gentlemen, is merely a chemical reaction which can be made to go backwards or forwards depending on how much of the ingredients, what proportions of the ingredients. Now, technically speaking, or among chemical demonstrators, it's called a clock reaction, you see. So what we're going to do, and what I'm going to tell you, is that iron sulfate, you see, iron 2+ actually catalyzes the clock reaction. It can make it go faster. So what we're going to do, we're going to make up two identical mixtures containing iron containing 100 cc's. If you can, Dom, if you can do 100 cc's of thiosulfate into each beaker, I will do 100 cc's of iodide into the big beaker, okay? And maybe Marjolaine, if you can do 100 cc's, oh, we need 100 another measuring cylinder, damn it. We'll get one in a second, dear Marjolaine. We'll rinse this out. I can ask you to do that one there. So 100 cc's of it's approximate. Don't have to worry about exact quantity, but we're doing this to show you what's known as a fair test. Yes, into each, 100 cc's there, actually, and then we've got to do it into the other one. I'm so nervous, I might get this thing rolled up. Let's just quickly get my one. Et voila. There we go, there. Now, Marjorie, if you can quickly, using that, just pour in 100 cc's of hydrogen peroxide into each of those. Thank you very much indeed. 100 cc's of hydrogen peroxide. Thank you very much indeed. Now, what I'm going to do, I'm now going to add some starch indicator. 100 cc's of each and there. Now, so we add the starch indicator goes in here, one squirt there, and the starch indicator goes one squirt into here. Get it as reasonably close to as 100 as you can. It doesn't have to be exactly, but thank you very much indeed. That's one there. And we're now going to have our iron. Thank you very much. We're very close to it, Dom, but keep it. You're doing very well indeed there. These two are my guardian angels for tonight. They're wonderful. Thanks to them, I'm surviving this evening. Right, very good indeed. Thank you very much, my dear Marjolaine. That's wonderful. Now, what I'm going to do, I'm going to add a squirt of iron 2 sulfate into one of them, but not the other. You see, so just a few drops. Just look, a little. There, that's it. Catalyst, you do not require. Now, catalyst, as I say, speed up the reaction. So what I'm now going to do, I'm going to add these, the hydrogen peroxide together. You have all witnessed identical quantities being measured, and we shall then put them up, we shall stir them, and then we shall observe to see which one. This one should go faster because it's got the iron in. See, so ready, steady, go. There we are. And it takes up to a minute, you see. So there we have our two solutions. They are identical. Can we take these away, please? We've finished with those now. We can put these maybe up. Just keep them there. And we'll see when they turn. One of them, this one should turn blue first, followed by that one. Oh, there it is. You see, so there it is. And this one. So you see, this is an example of catalysis in action. So we've demonstrated that one might well. And we use catalysts are hugely important in the chemical industry. A huge amount of money is spent on research into developing catalysts for chemical processes. Indeed, all modern cars now have catalytic converters in their exhaust pipes. That's to remove harmful products. You see, this one's taking the devil of a long time, but it will get there eventually. Now, in the meantime, there it is. So you see, catalyzed, uncatalyzed. Our thing is rising here. Thank you very much, dear Dom. That's coming on now. In the meantime, this balloon, I think this is now ready to be launched. It's actually doing incredibly well. It's probably the best one we've ever done, and it hasn't overcooked yet. If you could kindly carry those away, that would be more than perfect, and that one as well. Thank you so much. So I'm now going to tie this balloon off. I'm going to detach this balloon. And tie it up. You see, this is a big challenge for me. And we're going to. It's full of the lightest gas in the universe, which is hydrogen, you see. And as I said, hydrogen caused a huge amount of excitement in the 1780s with balloons. I'm just tying it off here. I'm just tying it off. Et voila. And now what we're going to do, we're going to see how high it can go. Marjorie, you can have the fun. Launch it as high as 3/4 of the height up and then tie it off down there onto the weight. Is that okay? And I will in the meantime, so Dom, if you can sort out the balloon, I will in the meantime get on to the next experiment involving iron. By the way, please notice how beautifully this chemical garden is growing, you see. Now, you see they're beautiful. They're like literally live plants, and you will be able to come and have a look at these later afterwards, dear children. Now, we finished with these 3 bottles, so I can put the 3 bottles down there. I now wanted to move on to something completely different. Actually, not that completely different. It's still chemistry, but in fact, we're moving on into the field of alchemy. There are, the balloon is there. Wonderful, wonderful. Anchor it down, and we shall not be wasting that. Oh, I forgot one experiment, by the way. It's we may as well show you, and that's how to burn steel wool in oxygen, in pure oxygen. There's no harm in doing an experiment, even if it's slightly out of context or late. But I showed you steel wool burning. It is, by the way, highly flammable. As you saw, one spark will cause it to burn. And I have a gas jar here, which has been filled with oxygen earlier on. And I just wanted to show you how the steel wool burns in pure oxygen. So we're just going to, and I've got gloves on because this is a very, very brilliant flame. By the way, if it was possible to dim the lights down, then I think that, and I'll try and do, I'll tell you what, this should, one of the important things, thank you so much, brilliant, the balloon is fantastic. What we'll do is, I will just show you, we'll just put this, I'm going to plunge, and you'll see it should make a very, very bright white light indeed, and crackle away. So there is the flame, just a light. And there you see sparkling away in pure oxygen. Now that's molten iron dripping off there as it continues to burn. Molten iron, iron oxide, and the whole thing is glowing, you see. So this is in pure oxygen. I'm pleased to tell you that Michael Faraday, who used to lecture here one of the greatest scientists of all time, used to do this exact experiment. So the time has not changed. It's still important what we learn, you see. And the fact is that the oxide there, which is made, is a solid, in contrast to the oxides made here, which are carbon dioxide and water vapor, which are vaporizing up into the atmosphere. So pure oxygen, obviously, supports combustion far better than air, which contains 20%, which is what we're demonstrating here. You see, it continues to rise. And the reason why it's rising is because the iron wool is reacting. Now, I wanted now to move to a slightly a different experiment, but we're still on the reactions, the chemical reaction of iron, and I have a bag of nails here. I have a bag of nails, and I have a pair of scissors, and I just wanted to pour some nails into here, you see, pour some nails into my container there. And I also wanted to pour some more nails here, some different nails there, and also stick this in here. Now, what I'm going to demonstrate for you is an experiment which has actually been known for many, many hundreds of years, but it's the interpretation which is complete. I'm pouring it onto a solution which we today call copper sulfate solution, but for many, many hundreds of years, it was known as blue vitriol. And I'm going to let it sit there for just a few minutes because I wanted to tell you that this sort of experiment, which you're about to see now, was an experiment with which people have been familiar for many, many hundreds of years. And it's very, very spectacular. Now, the sort of people who used to conduct experiments hundreds of years ago were called the alchemists. The alchemists were people who believed in the idea of the four elements, earth, fire, air, and water. They believed in ideas of transmutation, that one element can change itself into a different element. They didn't so much believe what they saw. They believed what they had been told was very, very important. They believed in knowledge handed down from the ancients. And for instance, the legendary founder of the alchemical arts was Hermes Trismegistos, Hermes the thrice great, who wrote down an emerald tablet with 13 rules of how matter changes into different substances. And the alchemists, using those rules, attempted to interpret all the observations they saw, and furthermore, they conducted their own program of experiments. Their program of experiments was very noble. They wanted to make medicines which would cure you and make you live forever. They wanted to find out the secrets of life and death. How are people born? How does reproduction occur? Is it possible to get people or animals and plants that have died to come to life again? Experiments in palingenesis, the experiment to make the philosopher's stone, the magic transmuting agent which could turn base metals into gold, but not for the sake of becoming rich, because the alchemists saw gold as the height of perfection. It's a metal which never tarnished, and they aspired to that. They were also profusely religious people. They were deeply spiritual, and they used to pray profoundly, hoping that their experiments would come to a success. They used to utter prayers like this: Domine non sum dignus ut intres subtectum meum, sed tantum dig verbo et sanabitur anima mea. That was a prayer begging Lord to purify them in order that they could conduct their experiments and get better results. Now, if I now decant for you our copper sulfate solution and show you what's left inside, you will see the sort of effect that, oh dear me, you see I've poured it on a beaker which I didn't have enough volume for. Silly Szydlo. Never mind. Here we are. This is the important thing. You see what happened, an apparent transmutation. This experiment has been known for several hundreds of years. And what they believed that they were achieving was they were actually transmuting a base metal into a more noble metal. Now, Dom, can we kindly ask you, because I've made the usual mess. I've got the wrong beaker. I hadn't thought that one. I'll just pour it off into here. This is now waste. If you could kindly take those away. I'm just going to mop up the mess I've made here. Thank you very much. That's most kind of you once again, etc. I'm just going to put all these things into the bin here. We'll have a little tidy up, and then we'll tip our nails out and just have a quick look at them here. Thank you very much indeed. And we should be able, I know what we can pour. We can pour the remnants of our solution back here, and we can go here. So when these nails, you see, and when our sheet appeared to be turned into copper, they believed that they were getting closer to their ideals. They thought that they're on the way to success, you see. But what I wanted to tell you, of course, in modern chemistry, this is, of course, a thin plating of copper that we've achieved here. And what we've actually conducted is something which is known as a displacement reaction. And we can explain this. Iron plus copper sulfate makes copper plus iron sulfate. So we're back to making our green vitriol, which we have in here, you see, in the form of beautiful crystals. And I wanted to tell you that this is not only called the displacement reaction, but it also has another type of name. It is called a redox reaction. It's the same reaction, just a different word for it. What I wanted to show you now is this same reaction, but done in a slightly different manner, and we'll be looking for something other than just the coating of copper. I have here a large quantity of iron filings. These are fine iron filings. I've poured them into there. It's once again, and I think you can all understand, this reaction will happen quicker than that one there, because this is powdered iron, therefore it has a larger surface area. So I'm going to pour in my copper sulfate solution once again, and the reaction will be exactly the same. Iron plus copper sulfate makes copper plus iron sulfate. Let me just swirl this around here. Now, dear children, the important thing is, can you see it's going green? We're going green. We've got to the majority. We've got to actually a huge amount. Right, with 40, 50. Now, can you see there's a huge temperature rise? Huge temperature rise here. What's happening is here, the copper is at the bottom, and you'll notice it's almost boiling. Now, the important thing is this reaction is exothermic. It's giving off a huge amount of heat energy, and that is now registering 40, 50 degrees centigrade. So here we have the same reaction that you saw there, but this time I'm monitoring an energy output. Now we can also get exactly the same reaction, believe it or not. It produces not only heat energy, but it can also be made to produce electrical energy. So what I'm going to do is set you up the same thing here, a voltmeter here, and show you the production of electrical energy here using our two substances, iron sulfate and copper sulfate. Now, if you could just get me some a piece of that white tissue, please, and I'll make a quick salt bridge. Actually, I don't know where I put my potassium nitrate solution. It should be somewhere. Yeah, that's it. That'll do. That'll be fine. Copper sulfate in here, and we can actually get another type of energy, which is electrical energy. So we've had heat energy produced, and now electrical energy. So I'll take a piece of this tissue here, and we make a salt bridge by bathing it in potassium nitrate solution. So if you don't mind, this stuff's totally harmless. Just going to there. And this is what is an inert substance. It's essentially making a very simple electric cell. So we're just going to put this in here like that. Put this in here like that. We're going to connect our positive electrode there. And please watch carefully when I connect so there's one there. And hopefully, whoops-a-daisy. Dom, can you come and one of you just hold this for me? I'll tell you what, if we just hold this, put that one on there. let's not have our back to the audience if we can. So if you just stand to the... Now, my dear, if you connect that to the iron electrode, you should all see, hopefully, 0.3 of a volt. There you go. And you see, so what we're showing, so there, what we've demonstrated, you see, is exactly the same chemical reaction. First of all, interpreted by the alchemists as a process for making a noble metal from a less noble metal. Then we've seen it as an exothermic reaction giving off heat energy. And finally, we've come to the most remarkable demonstration that it actually is making electricity as well. Now, the reason why it's making electricity is because there is a transfer of electrons. And that's the most sophisticated and difficult part to understand. And the person who first conducted these experiments was a great Italian scientist, Alessandro Volta, in about 1800. And he was the first person to make electric cells. Thank you, we finished this. We can take all this stuff away. And if we can now start getting ready, the thermite cage, please. Thank you very, very much indeed. We're now, so I've shown you now some examples then of redox reactions. Don't rush, Dom, take it easy. I'm sure we'll carry on even if everyone else leaves. We've got to have a wonderful program. I'm very, very keen to get through these. I love doing these experiments. You must excuse occasional mistakes. It is a huge hoo-ha setting all this stuff up. Now, what I wanted to show you next is an experiment which once again demonstrates this difference of reactivity. By the way, could I have the next slide, please? The next slide, please, which is, thank you very much indeed. If we set that up on there in the middle. The next slide, oh, yes, that slide there you see, that's just a close-up photograph. That's just a close-up photograph of iron having reacted with the sulfuric acid and left to stand for a few days. And that's a close-up showing the iron having gone rusty on exposure to air and tiny crystals of green crystals of iron sulfate. And then it's beginning to show those little white spots. Now, you see, alchemists would have thought that's fungus growing or some sort of growth. It is, in fact, the phenomenon of efflorescence. If we can have the next slide, please. This shows you the electrochemical set. This is just a few of the elements you see lined up in order of reactivity with the top of the bottom, potassium, calcium, sodium, magnesium, aluminium, zinc, iron, hydrogen, copper, silver. Now, this series was first devised by the Italian scientist Volta, and he didn't attach specific volts, but the effects of the different metals on his body. He used to connect up silver and zinc plates, and then connect the wires across his forehead, across his eyes and things, and he used to get horrendous shocks. And depending on how big the shock was, he then knew how far the metals were apart. But from a point of view of today, so what I've done is electrochemical reactivity series. The volts are given on the right just to show the volts they generate. And you see iron is minus 0.44 and copper is 0.34. We should theoretically have got 0.7 of a volt, but we got 0.3, which is fine. But what I wanted to show you next is the idea of aluminium reacting with iron oxide. Aluminium, you notice, is 2 spots above iron in this very, very simplified table. And what that means is any metal will displace a metal which is lower down from its compound. So what we've got in this beaker here is a mixture of aluminium powder and iron oxide, and I'm going to show this is a hugely exothermic reaction. It releases an enormous amount of heat energy, and for that special purpose I have built a cage here. This is a thermite cage here. Iron melts at about 1,500 centigrade, and what it does, that temperature will be reached here. In fact, this reaches about 2,500. It's an amazingly high temperature. So we have to have this specially prepared in a container like that. Now, this will release some smoke, by the way. The smoke will almost all be contained in there, but I do have to say, and Dom and Marjolaine will carry it out afterwards, you see, because they will take the cage off, put it on there, and then wheel the trolley away, and I will show you what's left behind. But this, you see, this beaker is made out of heat-resistant glass. It can easily withstand 900 degrees centigrade. I'm going to now pour into it. I'm going to make up a small quantity of a fuse powder. For this purpose, I need a small piece of paper. It's okay, I'll just take a piece of paper here. A small piece of paper here. A tiny amount of a fuse powder made from potassium permanganate there, and a tiny little bit of magnesium turning. Sorry, I've got the wrong stuff out here. I had brought some magnesium turnings. Do I have any magnesium? Where do I have? No, I don't. Too bad. I'll use magnesium powder instead. It's much more violent, but that's tough cheddar. we have to get on with things. I'm sorry about that. It's just setting this up took an amazing, as you can imagine. It was a thing, but we have to get through. Now, we carry on here, and as soon as this is over, we can then, oh, by the way, we have some beautiful minerals to show, because can we bring those lovely minerals, please? Excuse me. I wanted to show you, we have 3 wonderful minerals, which are, because this type of reaction is used for the extraction of iron in furnaces, and they are made from minerals from which the other element is extracted, and 2 of the minerals are, you'll be able to, these have been lent to us, especially for this evening, by the Natural History Museum in South Kensington, and there they are, and allow me just to show you briefly what they are. This here is popularly known as fool's gold. You'll be welcome to come and touch it. This is iron sulfide, and it's one of the ores from which iron is extracted, releasing hugely sulfurous fumes, and from which we can make sulfuric acid. This here is hematite, which is red iron oxide, which is the same stuff that I had calcined as Fe2O3, this characteristic thing. This was formed from the molten state at some stage. And this one here is magnetite, Fe3O4, the magnetic oxide of iron, which has got these beautiful crystals. Each of these 3 are minerals from which iron is extracted commercially on a huge scale. The annual production of iron in 2012 was 1.1 billion tons. This is the most widely used, the most universal. Thank you very much. Just take those back. In the meantime, on we go. Now this, I've mixed in some potassium permanganate with a tiny smidgen of magnesium powder. Now that will make a very, very bright flash, but it should set our mixture off, which is a thermite mixture, etc. Now, as I said, I'm a bit disappointed I didn't have my magnesium turnings. Right, so here we go. I'm going to now set this off, though, with another fuse powder. This may not work, I have to say, because I'm not sure that I've got the right fuse powder, but one just has to proceed on. So I've done what I think is a sensible amount of each. I'm going to, because of the extreme violence of this reaction, it takes about 30 seconds, by the way. Once I set it off, you will see a bright flash, you'll see a flash, you'll see lots of smoke produced, and then we shall then be able to inspect, hopefully, the product. Let me just have this, and this here. I'll have all my relevant tongs, and so I'm going to pour on a small quantity of glycerine, which will ignite, which has a 30-second delayed action response, so it's not immediate. There we are. Please take your time. Don't hurry. It's about 30 seconds. Now, if you both stand back a little bit, what we're going to see, hopefully, is a bit of a thing, a bright flash followed by, and there goes our thermite. That is white hot, 2,500 degrees centigrade. It is steel. It is iron being made. Now, what we're going to do is we're going to examine the products in a second. With Marjolaine and Dom will very carefully lift that off. Thank you very, very much indeed. And carefully wheel it out. That's very, very good indeed. Thank you so much indeed. Just very gentle. And I will inspect what's in here, you see. And if you look here carefully, there you can see molten iron pouring out through the bottom, you see, and our beaker has got a hole which has gone right through it. What I'm going to do next is to examine. I should have a fireproof mat. It doesn't matter, I'll get one from here. I'll just borrow this brick for a second, and we'll just put this on here. We'll put this on there, and we'll just have a quick look at our sample of iron which we've made in there. It was molten. We'll just pop it into the cold water there and let it boil away. There it is, boiling and bubbling, and very shortly I hope to be able to take out a piece of solid iron. What's the other product, of course, is aluminium oxide. The chemical reaction is aluminium plus iron oxide makes iron plus aluminium oxide. That should by now have cooled down to a satisfactory temperature. We'll be able to pull it out, and there we should have a piece of iron at the bottom which we'll use a magnet to pick up. Have we got, there's a small bar magnet somewhere. Can we now fire up, please, the steam engine? Thank you very much. Is something catching fire? There we are. There's our piece of iron, you see. So there we are. There's our piece of iron which we've made. And then no, this is just so it's a successful reaction, you see, demonstrating the huge power of chemistry. Now, Marjolaine, we're going to now go on to the metallurgy and the technology of iron. And what we can do in the meantime, dear Dom, is we'll let this cool down for a little bit, okay? I just want, while Marjolaine's getting the steam engine going, Dom will fire up the train set. And then we've got also the Meccano model to show you. Just a few little bits of pieces. Yes, please. Everyone knows that the Industrial Revolution was a period of the 70s, roughly 1700 to 1850, something like that. It was a time when a huge amount of progress was made in our understanding of science and technology, and masses of power was converted usefully. And that was all thanks largely to the strength of iron. And not only that, but our huge understanding of the principles of the reactions and how steam is produced and how it expands, contracts, a huge amount of chemistry, physics, metallurgy, all going on at once, gave birth to the Industrial Revolution. I've got a whole load, I've got just four books here, anyone who wants to look at, hugely interesting, beautiful pictures, illustrations, and so forth. The train, this is a train, just a model railway set. This is models which were very fashionable in the 1950s, you see, and a locomotive there. You're more than welcome, by the way, to come up and have a look at it later on. Here we have a model of a live working steam engine, which Marjolaine will set up. It takes a few minutes, so please don't expect results. But Marjolaine, could we just show us the Meccano while we're waiting for that? Could you please show us this? This is a Meccano model of the type that was very fashionable. Meccano sets were fashionable in the from the 1920s right through till today. But their heyday was sort of 1930s to 1950s. And Marjolaine has wound up the motor, and this is a working model. It took her several hours to make, by the way. It's not easy to make these models. And another run there just to show you. There it is. So a working model, and what the Meccano sets could do, they were all made out of steel, which they represented items of technology which people use on an everyday basis. The people who were responsible for steam engines, by the way, there's a huge history. May I recommend that you visit the Science Museum if you haven't done so already. Fantastic exhibition on the ground floor of steam, the history of steam power. It goes back to about 1700 with Thomas Newcomen and the condensing steam pump. The reason, by the way, why pumps were made in the first place, why steam power was developed in the first place, was to lift water out of mines. We have always relied hugely on mines for minerals for which we can make metals and all sorts of stones, cements, and other such like substances, also jewels, and so forth. So mining has always been a part of the great human tradition, and the deeper you go, the more likely that mines were to be flooded. So there was always a need for pumping out water, and that was the main reason. Are we ready almost to go? No hurry at all. I will keep them. They should be ready in a couple of minutes, and Marjorie has well tried and tested this. So steam engines initially worked on, they were reciprocated. The pistons used to just go up on one side, up on the other. There was no pressure involved. They were called condensing atmospheric engines. After about 1800, James Watt, brilliant Scottish engineer, came and developed more efficient technology for condensing the steam or for building up pressure. And he was the first person who actually started making instead of them just going up and down to pump up, he actually made steam engines where a wheel was turning, with an example of which we've got here. They were static steam engines. Now, these steam engines covered the whole of Europe. There were thousands of them everywhere. And you can see, as I said, several of them are on display, even full-size ones at the Science Museum. But this is a model which demonstrates the principle. The principle is as follows. The water is boiled in a boiler, and this is where iron comes in. Steel iron has always been the strongest, easily available metal, and boilers were made from steel, and all the components, the engineering components, the crankshafts, the conrods, everything was made out of steel. And that is why it is so ubiquitously in use. And the largest mine of iron today, I believe, is in Brazil. Huge area, and they go several, it's an open cast mine, several hundreds of square miles. And iron continues to... Now, please notice, our experiment is 100% successful. The water has gone right up into the flask, and it will fill, as you probably know, about 1/5 of the air is oxygen. So this is a 1 litre flask. We'll eventually have about 200 cc's of a coloured liquid in there, which will have, by the time that particular portion of air has been used up. Now, are we getting there slowly? No trouble at all. Right, in that case, carry on, my dear. We'll move on to the next topic, which is magnetism. And I just wanted to tell you that around the end of the 1700s, there were two huge advances in science, one in chemistry and the other in physics, concerning invisible things, invisible phenomena. In chemistry, it was the chemistry of gases. They were invisible, and people for the first time were able to identify gases, recognize them, and test for them. That was one invisible. The other invisible phenomenon, can we have the balloon experiment just to show, please? Have you got that? There we are, the balloons down there. The other invisible phenomenon, which had been known for thousands of years, was this one here. And that is what you all know, and we're going to now show you what happens. Invisible forces. The balloon is now sticking to the door. That, dear children, is what we call static electricity. So electricity, static electricity, was one phenomenon, and the other remarkable phenomenon was the one that we have here, and that is a magnet, and a magnetic phenomena. And it had been known, so please demonstrate it. I'll carry on talking. Please demonstrate, my dear Dom, the effect of the electric current. Once you've got it, I'll tell everyone what's going on. But the fact is that magnetism was something which was of great interest. People knew, they knew in nature that lodestone, which is actually the black iron oxide that I showed you, those crystals, Fe3O4, is magnetic. And people had picked up these stones, and they were used by Chinese explorers thousands of years ago. They were used throughout the world. We know, we have evidence, because they always pointed in the same direction. We now know that's called magnetic north. And that lodestone, but that was a mystery. People didn't understand it. William Gilbert published a book in 1600 of his theory of magnetism. We're going to try out to see. There we are. The steam engine is ready to go, so I will interrupt, and Marjolaine will now turn on the steam engine. Hopefully it'll fire up. It may take a little while. Now, notice, could we have the lights dimmed so you can all see what our steam engine is achieving? It's got a little light there. This shows the interconvertibility of energy. This was one of the greatest triumphs of the human race, was to harness the energy from burning to produce mechanical power. That's what happened with the steam engines. Thank you very, very much indeed, Marjolaine. That's absolutely wonderful. Notice the splendid steam coming out, etc. So this is a model steam engine, the real thing. The boiler, needless to say, made of iron and steel because of its toughness. Thank you very much, Marjolaine. Now, Dom will quickly demonstrate. I have here a beautiful compass here, which has a magnetic needle, and it is very, very sensitive to magnets which are brought around it. And Dom will try and demonstrate for you now one of the most important breakthroughs in the link between electricity and magnetism. It's an experiment. You could see it turning. You can see the needle is turning. This is an experiment which was done by Ørsted in 1819, and it linked the idea of an electric current to magnetism. Now, this was the greatest triumph of the great Michael Faraday, supreme experimenter. Michael Faraday, who, carry on with your next experiment while I just say a few things, a demonstration of a simple electromagnet, because Michael Faraday, who worked in this precise building, it's thanks to him that we have generations of, we have electricity being generated, the alternator, the electric motor, that was all Michael Faraday's work. And what Dom's demonstrating is a simple electromagnet, just a coil of wire around, and if you disconnect it, they all fall off. That's the point to show. If you disconnect the magnet, then they fall off. So that is a simple electromagnet made with a 1.5 volt battery. Now, dear children, just to show you how modern technology, that's a simple elementary electromagnet, how modern technology has moved forward. We have here a magnet, we have here another electromagnet. I'm just going to move it into a slightly brighter position here. And this one here, what I wanted to say is an electromagnet which uses modern technology, which uses one battery there. It's exactly the same battery, but this is capable of lifting 50 kilograms. Now, we've got just a, please, you'll demonstrate it now. We've got just a 20 kilogram piece of rail, and if anyone wants to come and try it afterwards, you're more than welcome, but believe me, this is very, very heavy indeed. The point of the demonstration is to show you how very, very efficient today's electromagnets are, from the day when Michael Faraday was doing those experiments there to today, where we can get, and they have huge application in industry, electromagnets. This is the reason why that is so efficient is because of the design of the magnet and the number of coils to give the maximum magnetic flux there. Now, on the subject, we're now, is it onto metal? We've almost finished. We're getting close. Are we getting ready for the welding? If you could just quickly bring in the welding gear, a very short experiment on welding. I hope you don't mind, because this is a very interesting thing. I just wanted to tell you a little bit about steels. That steel, the science of, may I just give you, this book here, published in 1888, is entitled Electricity in the Service of Man. This is written by a German author, huge amount, fantastic pictures. Just look at the pictures. It's amazing how much was already happening then. This book, Great Engineers, I'll quote from that later on. And here, Metallurgy by Sir Robert Hadfield, one of the greatest metallurgists, a profound person, supremely interesting book, masses of interest. And as I said, the pictures in all of these books are quite fantastic. Now, what I'm going to do is to demonstrate for you very, very briefly a little bit on welding, then we'll have a bit on metallurgy, a bit on blood, and then we're finished. I hope you don't mind if we're running over by a very, very considerable margin. Unfortunately, I haven't done this demonstration before like this with all these things, but I think coming to the Royal Institution, one must show the best of what humanity can do in terms of giving you an experience to remember something positive. Now, so here we are. I require a brick. Where's my brick? Watch out, hot? No, not hot. Okay, thank you very much indeed. Yes, it is hot, but it doesn't matter. Now, what we have here, now I'm going to show you very quickly, because you see, all of these things I was showing you, all of these machines, steam engines, bridges, the whole engineering world of iron, steel and technology, you have to join the iron together with something. So you have to join it together. So the most ancient technology was to use rivets, which is you make a hole and then you sort of knock together two bits at the end of a steel rod that you put through, and it holds it together. And rivets are still very used. They're used on aeroplanes, they're used in the naval engineering, and they're used throughout the world. Nuts and bolts used, but the point is, with both rivets and nuts and bolts, they are both intensely labor consuming. So they take a long time to screw the nut and the bolt or to whack the rivet together. So a technology was developed at the end of at the beginning of the 20th century, which is, oh, by the way, you can sprinkle some iron magnetic powder while I set this up, you see, just to show you. These were experiments, once again, invisible forces, but we can have a demonstration for you. Marge here will just show the beautiful pattern, which some of you are familiar with, but I just find it so beautiful. Sprinkle some iron filings on a magnet, you see, and it shows you a field of magnetic flux. Now, what I'm going to do, I'm just going to show you the power of the technology of welding. You see, welding became possible for two reasons. First of all, the chemistry had been understood. So people were able to make gases and collect them, which had a fantastic lead. So look at that beautiful pattern. Those are the fields of force, invisible fields, which we can't see normally, but the iron filings show them there. But what I'm going to show you now is I'm going to show you very briefly the technology for joining metals together, which is used today. There are various types of welding, and oxyacetylene. It was possible because, to start off with, as I said, it was possible to make the gases oxygen and acetylene and store them in large industrial quantities, but just as importantly, they were able to make cylinders which were strong enough. These cylinders are made of steel, you see. So, having divided that, they then sought to find out gases which would have a sufficiently high temperature when they were mixed to be able to melt iron. Now, just for your information, your domestic cookers, the flame there burns at about 600 or 700 degrees centigrade, you see. So that's, by metallurgy standards, that really is a very low temperature. I won't bother with a match. I'll just use my candle, which is burning fire easy. So please, so this is going to be pure acetylene catching fire. If it comes, oops, a daisy, is that possible? It should have. There we are. So there's pure acetylene. Now this is acetylene, which is a gas, which is burns with a, hang around, it's something's not quite right. Shouldn't be going down. That's turned off. Okay, I think, let's just check our cylinders. Yeah, that should be okay. Right, so we've got now, this is pure acetylene. C2H2, the chemical formula. It burns with a very luminous flame, giving off quite a lot of soot, as you can see, going up. Now, if we add oxygen to it, as I very shortly will, please excuse me, then the flame will gradually increase in luminosity, but will then become a very, very beautiful, intense blue color. And this temperature, the tip of this flame, is about 2,500 centigrade. So at the moment, that's luminous, but it should gradually turn blue as we increase the proportion of oxygen. So we're now getting a typical flame which all gas cookers have and Bunsen burners have with their flame holes open, and there it is there. Now this flame is, can reach a temperature, as I said, of 2,500. Oh, dearie me. You see, because I'm trying to do too many things. Let me put my gloves on first. We'll put my gloves on first. Okay, I accidentally turned the whole thing off. That wasn't very bright, was it? Never mind. We're back in business again. Let's put on our acetylene, just make sure that, right, that would help if that was screwed in properly. I hadn't done that either properly. Right, as you can see, this was all set up in a hurry, but, try again. There we are. Right, so there we are. We're burning, we're back in action again. Turn the flame down to a sensible height there. Let's get our oxygen. And now I'll just show you how very, very hot this can get indeed. I'm going to, first of all, heat a test tube, which is made of heat-resistant glass, and that melts at 900 centigrade. I just tried to demonstrate for you the phenomenon of plastic flow. So there is our flame, and if we play that flame on the test tube there, you'll notice a beautiful orange color. Now that orange color is due to the sodium content of the test tube. The test tube is made from basically a glass which contains silicon dioxide, sand, and I'm just going to see if I can get plastic flow where it will actually fall but not reach the ground. It's a very tricky one to do. We'll see if we can do it. We're melting it, but it should, please watch. There we are, just about. There it is. There we see a piece of, you see this here, what I've demonstrated is plastic flow in glass, you see. So this is, you see, glass which we've just about managed to catch. Now, what I'm going to do, I'm going to actually now attempt a welding experiment. Well, we can take this away, please, Dom. Please excuse me. I'm going to attempt, rather than do something boring, I'm going to do something a little more interesting, which you may not be aware of. And I'm going to start off by sprinkling some 2p coins, which of course are made of copper. However, if we take a magnet, do we have the permanent magnet here, my dear Marjorie? Oh, down there, my dear. Could you please get me the magnet? Dear children, 2p coins are made of copper, you see. Either one of these will do. Yeah, thank you very much. Now, you see, so copper is not magnetic. Copper is not attracted to a magnet. You see, there it is. That's not attracted. So what's the point of demonstrating this, you see? But hang around. That one is magnetic, so I'm not quite sure whether I'm demonstrating this correctly. So that's a copper coin, but it's actually not copper. This one is, that one is, hang on, that's magnetic, that one is, that copper isn't magnetic, that is, hang around, this is very odd. That one's magnetic, that one's magnetic, that one isn't, that one isn't. So what I'm demonstrating, dear children, is a most interesting thing, is that actually 2p coins can be made either of iron or of copper, and this is a cheat, you see. They're not actually made of copper. They're made of iron, but coated with a very, very thin layer of copper, you see. So, because they're made of iron, and the reason why this happened was in 1989, it became more expensive. The amount of copper used in the amount of copper used in making a 2p was more than the 2p pence was worth. So people would melt down 2 pence coins and get rich that way. Not a very economical way, but nevertheless. Now, could we have the beaker of water with sand in it, please, Dom? You remember the one where we put the thermite mixture in? Thank you very, very much indeed. What I'm going to do now, I'm going to show you that these are made of steel by creating a very, very unusual coin. If there are any coin collectors here, I'm going to make an 8 pence piece, you see. So I'm going to weld my 4 coins together. Thank you very much. No, Dom, there was, yeah, that's fine, that's fine. Actually, no, you're right, on the table. On the table, Dom. Dom is really quite an extraordinary character. They're both amazing characters. Now, in order to weld them together, I need a welding rod, which I've got here. You see, so this is, by the way, very, very difficult welding under any conditions, let alone at the Royal Institution. But I think, again, in the interest of education, we must show you what the possibilities are. Where do I have my goggles? Oh, here. By the way, I have to say the goggles are mainly to enable you to see better. This is not an intrinsically dangerous process like arc welding or MIG welding, where the temperatures reached would damage your eyes. This is merely so I can see better now. Now, I would probably have to stop talking. What I'm doing, but I'm going to carry on talking because I can't stop talking. Now, what I'm doing, this is a very tricky operation. I'm heating up the 2 pence coin, which is made of steel, as I've demonstrated, and I have to get it hot enough in order that I can melt this rod which I'm holding. Right, I've made a 4 pence piece. We're now on to the next one. You have to heat up, you have to develop sufficient thermal capacity to actually melt the steel. It has to actually flow. And the trick is, if you melt it too much, then the whole lot just catch fire and burns away and you're left with nothing. So there's quite a fine margin. There's not much scope for error in this, but we've got a 6p coin at the moment. So, and the thing is, because iron and steel are so very, very, very strong, then the joint is very, very firm. And welding has huge applications in industry. I think we're there, actually. Now, I'm going to put this down here, turn these off quickly. 1, 2 there. Now, what we do now is we pick up our 8 pence coin and we lob it into cold water to cool it down. And now we have a look to see our product. Woof, that's quite hot. There we are. And there we have, ladies and gentlemen, an 8 pence coin. This will be very useful for anyone. Can you imagine if you've seen the shop? If you see in the shop something you want to buy for 8 pence, instead of fumbling around, say 1p, 2p, just say 8 pence. There it is. You see, wonderful. So you see, we can always invent. Now, thank you so much. We're now ready. Thank you. Let's just move, if we could take this out indeed. Thank you very, very much indeed. What was next on the list? We're almost at the end now, aren't we? Bits of metal. Oh, I know. Metallurgy and then the fine art one. Is that it? Is that right? Is that right? Is it metallurgy? Right. Dear children, I've very nearly finished. Just a few little bits and pieces. You see, the different types of carbon, different types of steel depend on 2 things: how they have been heat treated in the foundry, and secondly, how much carbon they've got in. A typical mild steel contains about 0.1% carbon, not much at all. And I've got to example, mild steel is this thing here. It's what most things are made of. Here I've got a piece of cast iron. Cast iron is used hugely. It's strong, but it's very brittle. Whack it one with a hammer and it splits apart. Here we have tool steel, high carbon steel used for cutting tools, etc. And here we have spring steel. Spring steel used to store energy. You wind it up, and I've got my beautiful pocket watch here, which tells me we're way over the, oh my goodness, almost 2 hours. The 5 to 8 to 10, that's wound up with a spring, you see. And another application, you see, people have made use, we can make use of springs in musical instruments. The piano, for instance, has steel wires which vibrate, but the mouth organ has steel reeds. So I'll just play a little Polish folk tune on this. Let's get it right way round first. Thank you very much for that. Spring steel in action, you see. Now, we've got almost, I'm going to show you quickly another heavy duty. Let's do the starter motor. The starter motor quickly. The starter motor and then film. Is that okay? Have you still got the energy? We've got plenty of energy. I'm sorry if some of you have to leave early. Dear ladies and gentlemen, Michael Faraday invented the electric motor. By the way, could we have, please, the couple of slides? Michael Faraday's original electromagnet is here. That's one of his original electromagnets. It's on display at the Royal Institution here. They have a fantastic display. And I cannot overemphasize, one could do a whole talk on Michael Faraday, his life and his work. But he was a profoundly humble man. He wanted no glory. He just wanted to serve mankind. He was really, and please, the next one, the first ever electric motor. Doesn't look like an electric motor, but that thing spun around. There was mercury in there, and each of that little needle, it spun around a central thing in a central pool of mercury when the current was passed. I don't know how it works, but the fact is it does. Now, I've got here, the honest truth is, this is an electric motor used for starting motor cars. Every single time you turn a starter key, what happens? Well, this is what happens. And that's a starter motor, you see. But the thing is, when the starter motor goes round, you say, well, what the dickens does it actually do? Thank you very much. Thank you very much. That's brilliantly demonstrated. I'll just show that. And now we'll connect up the thing. And show. So when you turn this, you see, you say, well, how on earth does that start a car? Well, I'll show you. We're now going to quickly construct a part of a car. I think it's very important that we have some beautiful, this is part of a car, this is part of a differential gearbox. Please pick up one tool and the other, and I'll get it. This is beautiful, by the way. All lorries have this, and all of this, and the Triumph Herald motor cars, these things from Triumph Herald's brilliant engineering, and the reason is it's simple, easy to take apart and put together, nut and bolt technologies. And the point is, all of these things are beautifully made, and they're mass-produced, mass production, which is the hallmark of today's industrial revolution. And what we're going to do is just to show you how it connects up. Now, this here is a flywheel, you see, so when the starter motor turns, this tiny gear here engages onto the flywheel here, and we'll just quickly build part of a car to show you. There it is. I will hold this, and this is, by the way, this here you will all recognize, of course, is a crankshaft. It's a crankshaft with one piston in it, and let's start. We'll just locate it, and I think it's very important in a lecture on iron and steel to build part of a motor car. After all, we all use motor cars. We all use motor cars on an everyday basis. We take them for granted, and Marjorie will now very quickly insert 5 bolts. There's a locating screw. There we go. We're in. Marjorie will quickly locate 4 set screws and then tighten them up. We'll be almost ready to drive off, but we'll be ready to do almost the final experiments, which I think is that right? It's the last one to go. Thank goodness, we're nearly there now. We're very nearly there. Please excuse me. There we go. Let's just tighten this up now. Here we go. Using a socket there, 5/8" socket with a T-bar on it. And this is the sort of thing we do at Automobile Society. We dismantle, we build things. And cars, and I cannot recommend the enjoyment of fixing something yourself. I think that everyone knows that the great satisfaction of doing something yourself, you fixed it, you made it work, and you feel it's a great sense. And a little bit of practice and anyone can do it. And there we are. Marjolaine has just connected the flywheel to there we are. And all of this is beautifully precision engineered. And do you know what's amazing is this tiny motor has enough torque to turn that whole thing over and get a car going. So there's that one there. And now we're on to the final demonstration of all. And that is, just one thing. And this is not a demonstration, you don't have to worry. But it's just to tell you about, of course, iron in biology. And of course, do you all know that we have about 6 grams of iron in our blood? We all have iron. It doesn't flow around in the form of iron filings. It flows around in the form of hemoglobin, the red colouring matter in our blood cells. And that iron plays a most important role in our physiology, in the way we live and breathe. Now, what we've got here is 2 hydrogen-oxygen balloons, and the purpose of this, you see, is to show the enormous resistance to heat of steel. This is a steel rail, and in it we're going to put a flash powder which consists of magnesium and potassium chlorate. Now that flash powder generates a temperature of about 2,500 degrees centigrade, which, if there was enough of it, it would most definitely melt our steel rail. But now, can we just quickly, we mustn't waste our balloon up there. You see, that balloon there is filled with hydrogen, and if you don't mind, I cannot bear the prospect of having a balloon filled with hydrogen going up. Now, I do repeat that these balloons filled with hydrogen, could you just hold it down there? Thank you very much. So there it is, you see. I'm going to, if I tell you what, we could just secure it somewhere, and I'll quickly light it with a burning splint. Just hold it there. It would just burn it off. It's not very spectacular, I have to warn you, but it's nevertheless, it's important that we don't waste good chemicals. So I'm just going to set fire on that. Oh, it mustn't set fire to these two. That would be a terrible disaster. These, by the way, are filled with a mixture of hydrogen and oxygen, you see, and they will make a very, very loud bang if the experiment works. So this is just a balloon filled with pure hydrogen, which we made earlier on. It burns with an orange flame. It's not particularly loud, but it's rather fun. There it is. So there it is. You see, that was our. Now for our very final experiment. Please. The final experiment. Now, may I please? I'm going to make up a small quantity of magnesium flash powder. Now, this, I have to warn you, does burn with an exceedingly bright flash. So, and sparks will fly. Sometimes they go a couple. Almost certainly, we may be sort of get ready to squirt water, okay, on anything. It'll catch fire. Dom, are you ready? Do we have another squeeze bottle? Doesn't matter. Just pour a beaker of water on it. But it should be okay. Now, I'm just sorry. Now, what we do is we mix this magnesium powder. You know, I'm so nervous. My eyes are frosted up. I just have to take those off. They steam up. I had 6 pairs of safety spectacles, but in all the hurry, I just don't know where I put them. Did I put one that doesn't? There's one that doesn't steam up. Thank you very much. These are very, you must understand, this is nothing. These have to be worn if there's sparks which are likely to go behind. These are not. These are just good for making, for sort of, liquids and standard laboratory work. The other ones are industrial, heavy-duty safety. But now, here's then our magnesium powder. Now, I've got to make sure that it's smooth, because if it's not smoothly powdered, then sparks are liable to go. So another sheet of paper, if you'll excuse me. Thank you very much, Dom. Thank you very much. Just a tiny bit here. And I have to be very careful. The quantities are, it's all slightly it's an art rather than a science, what I'm doing now, just mixing them together in hoping, and I'm just double checking that. Now we have to mix them very, very carefully indeed. Very carefully indeed. And at the end, what I'm going to show you is that even though hopefully there will be 2 loud bangs and hopefully there will be a blinding flash, this will still be intact, which is the main purpose of the experiment. Now, please excuse me while I now just hang around. I'm just going to pour them from one sheet to the other. We have to make the fuse powder as homogeneous as possible. There it is. So I'm now going to very carefully. Now, I do repeat, if there's anyone who's afraid, then I would definitely leave. This will make a profoundly loud bang, and also there will be quite a little cloud of smoke which will go up. But I've been reassured by the organisers that smoke alarms are fitted, and that the air will become very fit to breathe in a short space of time afterwards. So, now, I need some potassium permanganate. We use, as I said, potassium permanganate goes in here. Et voila, there we are, just a little bit there, and to that we're going to add some glycerine, and then I've got to actually show you that it's survived, but perhaps it will be good to have this is a very, very bright flash indeed, and if we dim the lights, I think that will be very satisfactory. So we'll have one. Now, I do repeat the warning. This does make a very loud bang. It does send up there'll be 2 loud bangs and a large cloud of smoke, and this will be definitely the last experiment. So after that, I will hold up, hopefully, and I wish you all a very good evening. I hope you've enjoyed learning something. Now, here we go. So there's our glycerine. Now, as I said, it takes up to 30 seconds before the mixture actually takes off. So we'll stand back and watch. My suggestion is you don't look at it directly, that you sort of look at it at a slight angle, etc. There it goes. So we'll watch out carefully. There it is. So have lights on, please. Thank you very much indeed. So there is our thing having survived. Thank you. Thank you very much indeed, Marjolaine. Thank you, Dom. Thank you very much indeed. We'll come out to the front and take a bow. Come to the front with me. Thank you very much indeed. Dom, come here. So there are my two assistants. My two assistants. Thank you very, very much indeed. Our very, very best wishes. Very, very best wishes. Thank you so much indeed. Thank you very much, Marjolaine.